Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to concepts of momentum and impulse. So, what we're looking at right here, we've got some sort of object here, doesn't matter what it is. And in my picture here, I've assumed that there's basically three forces on it, but this is just kind of representing any system of forces acting on an object. There can be 3, 4, 7, 100 million, doesn't matter. Now, any system of forces can be added together to find what we would call the net force. And remember, the net force is the vector sum of all forces acting. So if we were to add up all force vectors acting on this object, we would get some net force, which, roughly speaking, would be about down and right. It's not important for this video that this force be exactly in the correct direction based on the length of these vectors that I drew. I just sketched some vectors and put a net force in. All right. What is important here is the mathematics that we can apply to this thing now. So Newton's second law tells us that the net force acting on a system is equal to ma, or mass times acceleration. But the acceleration of the system can be written in different ways. In a college physics class, a lot of times I write it like this: delta v over delta t. Now I'm going to go ahead and keep putting the vector symbol over it. Or in the language of calculus, we can write that the net force is equal to m dv dt. Either of these are acceptable ways to look at Newton's second law. And an important thing to realize is whichever equation you're kind of thinking about, this delta t here can be separated from that delta v. We can multiply both sides. Same thing over on the left. I'm going to go ahead and just work with this equation right here. So if I take this delta t and move it on the left, and I'm going to drop the net, and from here on out it's just going to be understood that when I write force here, it's the net force. So when we have force times delta t on the left, on the right we have m times delta v. Now, delta anything is equal to v final minus v initial. So this right-hand side can be written your final velocity minus your initial velocity. I just continue to put the arrows over and remind us these are vector quantities. These terms, if you look at this, m times v final, m times v initial, the product mass times velocity has a special name. It's called momentum. Because it's a scalar times a vector, momentum is also a vector. The units on momentum would be the kilogram meter per second in the SI system, or the slug foot per second in the English system. This quantity on the left has its own name as well. It's called impulse. Impulse is force times time. And again, because force is a vector quantity, impulse also is a vector quantity. If we take this equation, if we look at it, what this basically says is the impulse acting on a system is equal to this. Well, this quantity, mv final minus mv initial, represents the change in momentum of a system. And impulse is the quantity that changes your momentum. It's a little bit like work energy principles. Work is force times distance, and work changes your kinetic energy. So they're somewhat similar. However, big differences to realize. Work is force times distance, whereas impulse is force times time. That's one big difference. So work has units of Newton meters. Impulse has units of Newton seconds. But another major difference is this: impulse is a vector quantity, and so is momentum. In work energy methods, work is not a vector, it's a scalar. Same thing with kinetic energy. All right. This equation, it's pretty easy to show that by multiplying by m and rearranging this, that basically says mv initial plus f delta t equals mv final. What this equation is saying is that when you take a system, if you know its initial momentum, mass times velocity, plus any impulse added on the system, now you have the final momentum of a system. So I think, this video is just meant to be an introduction. I think I'll make some other videos here going through examples and talk about, the most useful parts of momentum. But I will point out one thing right now. The last thing about this video to think about is this. What if the net force acting on a system were zero? What would that tell us about the system? And I want everybody, watching this video to pause it, think about that for just a moment. All right, I'm going to come back here now. So if the net force on a system were zero, the initial momentum of the system would equal the final momentum of the system. That's a very, very handy thing to know for analyzing a whole class of problems called impacts. And I think what I'll do is I'll talk about impacts in another day. Have a great day.